Today, we will discuss different solder-free technologies for PV module interconnection. Two aspects will be covered: electrically conductive adhesives in comparison to the standard soldering method, and mechanical pressure modules. Let us recap the most common method of interconnecting solar cells within a module. Our example starts with a single solar cell. Coated copper ribbons are then soldered to the front side busbars of the solar cell. The ribbons are then soldered to the rear side contacts of the next solar cell. Then the process is repeated by soldering the ribbons to the front side contacts of the next set of solar cells. For the soldering to work, the ribbons need to be coated with lead, which is a toxic element which we would like to avoid using from an environmental impact perspective. One lead-free alternative is using electrically conductive adhesives, or ECAs in short. ECAs consist of a polymer adhesive matrix which holds the contacts together. This polymer matrix is filled with conductive particles to provide sufficient electrical conductivity. Advantages include a low process temperature and the lead-free nature of the ECAs. One disadvantage is a higher silver consumption compared to traditional soldering methods. Conductive adhesives can be applied to many types of different solar cells, including alu-BSF, PERC, silicon heterojunction, IBC, MWT, and busbarless cells. ECAs can also be used with various kinds of interconnection technologies, including shingling and back contact solar cells with conductive backsheets. A mechanical pressure module replaces the typical EVA encapsulation with a natural gas. This gas has a lower pressure than the environment. To keep this under pressure, the edge of the module needs to have an airtight seal, which is adopted from insulating glass technologies. This module type is also known under the name of NICE module, which stands for New Industrial Solar Cell Encapsulation. The fabrication process starts with glue deposition on the rear glass or backsheet of the module. Second, the solar cells and metal connectors are placed on the glue. Next, the external connector is positioned, and in the fourth step, the deposition of the edge sealing material on the front glass or front sheet is done. The fifth step contains closing the material sandwich, and during the sixth step we apply a mechanical pressure to the front and rear of the module while the module is flooded with natural gas, which creates an underpressure of approximately 200 millibars inside the module. This module type has advantages and disadvantages. Optically, it has the advantage of the gas having virtually no absorption. However, the gas has a different refractive index, which increases reflection at the inner side of the glass. This can partially be resolved by applying an anti-reflection coating on both glass surfaces. Similarly, the cell anti-reflection coating needs to be adjusted to the different refractive index of the gas encapsulation. As for ECAs, the soldering-free and low-temperature fabrication is a major advantage. This also lowers the environmental impact of the technology. Due to not having EVA, various degradation modes related to EVA, such as browning or PID, are also not present in these modules. However, the edge seal needs to remain airtight for the whole lifetime. Not having laminated encapsulation also improves the recyclability of these modules as the materials are easier to separate. To recap this lecture, we discussed two soldering-free approaches to interconnecting the solar cells in the PV module. First, electrically conductive adhesives, which consists of a polymer adhesive matrix filled with conductive particles. The second approach is mechanical pressure or NICE modules. These modules replace the typical encapsulation material with a natural gas with an underpressure. This approach increases reliability and recyclability of PV modules, but requires glass with RSCs on both sides.